Here is our Blitz review of kinetics, focusing mainly on the integrated rate laws. Recall that we have rate expressions where we are just communicating the change in concentration of reactant or product per unit of time. Rate laws show the impact of a specific reactant concentration on rate. That is shown through the order. And most commonly, we have first, second, zero, and half orders, where lowercase k is the rate constant, and it is constant per the temperature and the reaction. Well, the integrated rate laws come out of knowing the order of a reactant. So what we need to be able to know from integrated rate laws. There are different equations that we associate with first, second, and zero order reactants. So we have to know which and then how to apply the equation, which equation and how. Which graph, which comes from how we express the concentration. It's in form of a line, and when we get a linear relationship between certain variables, then that backs up the order of the reactant. And also we can pursue the half-life of a reactant, which will differ if it's first, second, or zero order. So if we dig in. Now, the grand majority of reactant concentrations vary inversely with time. So we know that if we're starting with reactant, that with time, we're going to get an inverse relationship because, of course, the concentration plays a role on rate, and as your concentration is changing, your rate will continually change. And so we can't just tell the order of the reactant just from here. We just know that we're going to get this shape. But actually, if we get this shape, this inverse curve for concentration versus time, we know that A is not zero order. If A was zero, we just need A to be present. The concentration does not impact the actual rate. If A was zero order, the rate law would be Ka to the zeroth, which we know this is 1. So the slope that we'll get is from a linear line, and that actually is the value of our K. But what about the other orders? Okay, well, if we have a first order reactant and we integrate that, and we don't have to know how the integration happens, we just have to know the equation that we get. And we usually express it in this form. We get the natural log of A is equal to negative KT plus the natural log of the initial concentration of A. This is in the form of y equals mx plus b. So if we would graph a first order reactant of concentration versus time, this is what it'll look like. But if we would graph natural log of concentration versus time, we're going to get our linear relationship, and the slope is our negative k. Again, if we would graph concentration versus time for first order, we're going to get that exponential with negative growth. All right. We can express this a different way, rearrange the equation. Remember, we looked at this a little bit. If we would rearrange the equation such that the initial concentration divided by the concentration at time t, and take the natural log, that's actually positive kt. So this is just another version that we can utilize if you're more comfortable with that. Now remember, we talked about half-life, the amount of time it takes for half of your given reactant amount to have reacted away. Well, with the first order reactant, very, very, very important, the half-life is constant throughout the reaction. Half-life in terms of a first order is only impacted by K, and K is constant if your temperature is constant and your reaction is constant. So if it's first order, that's our half-life. Here is our integrated rate law, and here would be the conformational x and y that we need to confirm its first order. Okay, if our reactant is second order. Well, if the reactant is second order, then it will be a curve, just like first order would be if we do concentration versus time. If we would do natural log of A versus time, and it's second order, then we're also going to get a curve. However, if we would graph the inverse of concentration versus time, we get a positive slope, linear, and that's our K. Because when you integrate a second order reactant, we get the equation of 1 over A equals positive KT plus 1 over the initial concentration of A. If we derive our half-life, for a second order, the half-life is not constant. And I just want to make sure that I am referencing. Yep. And so our half-life is sorry for the delay, ladies and gentlemen. Oh, for heaven's sakes. I will include it to come. Sugar. If I'm not mistaken, the half-life of second order is A over 2K. Oh, goodness gracious. Very embarrassing, ladies and gentlemen. It is escaping me at this point in time, but we know that half-life is not constant. And actually, we were never asked, I have not seen a problem that asks us to find half-life on the AP Chem exam if it's second or zero order or half order. Actually, if we want to take a moment, the equation sheet, these are the equations that we are given as far as kinetics go. So we're given integrated first order, this is just presented a little differently, integrated for second order, just presented a little differently. And you see they're noting that the concentration of A is at time t, and only one half-life. This is first order. So you're normally not going to have to solve for half-life of second or zero. I would virtually say we can bet money on it. But you can just know that it's not constant and use that to back up any kind of justifications. Okay, so back to our zero order. If you graph concentration versus time and you get the linear, then we know it's zero order. And it is actually A equals negative KT plus A naught. Looks a lot like the integrated first order reactant, but without our natural logs. I have just these NIMSY pages from the review packet. If you want to pause and read any of this, this is just talking about, how if we're graphing concentration versus time, how reactant will look and products will look. And I talked about these in the last video. This would be referring to products that are being formed, because they're starting at zero, that have a different mole ratio. So we're making NO at twice, it looks like the rate of O2. Okay, as far as, integration, this is talking about, the different graphs that we would create and which graph confirms which order. To go back over zero order, if you want to pause and take a look at this, then we'll look at first order. If you want to pause, and take a look at this. And here's for half-life for first order. And this talks about second order. And you see they're not even giving us half-life because it's just so infrequently expected of us. All right. Now, something else just review briefly would be reaction diagrams. And we got introduced to these in chapter 4. They're showing reaction progress, and energy in some way is on our y-axis. So it's often potential energy, or it could be enthalpy. This could be, just blatantly energy. So if we are starting with reactant at lower energy than product, then we know it is endothermic. We have to invest energy, usually in the form of heat, to overcome the bonds breakage, and the new bonds that we're forming are not releasing as much heat. So we end up at a higher overall energy. The difference between reactant and product is the enthalpy change, which will be a positive value if we end up higher than we started. Now, the difference in energy from reactant to the top, the peak of the hill, that, remember, is activation energy. Activation energy is the minimal energy that must be invested, we believe, to start to break the bonds in the reactants and then get everything in position as it needs to be orientation-wise to form new bonds for product. We theorize that there's an activated complex, this in-between kind of species that's of high energy. That is why we have to invest energy to get every reaction to start. There's always some kind of activation energy. So what we have to invest is from the reactant energy to the top of this peak. This, we're ending up at a lower energy with products than we started. And so this is exothermic. And the difference in the height from reactant to product is our enthalpy, and it would be negative here, our enthalpy change. The difference from the energy of reactant to this peak, that's our activation energy. We can usually represent it with capital E for energy and then a lowercase a for activation energy. But you don't need to remember that. We can always note that. You can write it as activation energy. Now, if we were going in the reverse direction, activation energy would be from, if it's reversed, these are acting as reactant. So this would be the activation energy for the reverse reaction. And it would be endothermic in the reverse. So these, aren't necessarily flip-flop versions, but I think they're scaled kind of to be able to make that comparison. Now remember, the role of a catalyst is to lower activation energy. A catalyst is seen first as a species in an elementary step of a mechanism. So remember, mechanisms have multiple steps. Maybe A plus B gives C, and then C plus D yields A plus, let's say, F or something like that. A reaction intermediate is produced first in an elementary step and then later as a reactant, but a catalyst first as a reactant and then later as a product. So we say it's not chemically altered. Well, that's because it's used and then reproduced. But what we think is a catalyst provides an alternate pathway that is of a lower energy requirement to start. So we're still going to get the same products, but if there's not such an energy kind of hurdle to get over, then it'll be faster to produce those products. Now notice, a catalyst does nothing to change the enthalpy. It is just helping reactants to form products more easily because there's not such an energy hurdle to overcome. All right, so let's take a look at some example problems. This is from the NIMSY review packet. I think it just nicely touches on just what kinds of questions might come our way. Excuse me, but I'm going to show you some other questions that are really well done, that are very just good examples of what we may see come test day. Okay, so we are decomposing substance X, just this generic thing. It is first order. Please do not forget to really just look at the wording you're given. All right, and I'm given concentration versus time. Sketch the expected curve based on the label axes. It is first order. So, now remember, we are given these equations, but it doesn't say, this is first order, this is second, this is half-life for first. So make sure that you know that. Make sure you also know the graphs that we would generate if asked to reflect an order that we're told or that we ourselves found. Okay, so first order we know is going to be curved like that, but will be linear. Now don't worry, they're just asking for a sketch, so they're not expecting us to know the slope and that kind of thing. Okay, so you do not need to plot the exact data. Okay, write the rate law. It's first order. So, and it's okay, we understand that to be an exponential of 1. Explain how one of the two graphs can be used to determine the rate constant. It doesn't say to find it. Just explain how you would find it. So, K will be the slope of the natural log of x versus time, because the linear relationship matches the integrated rate law of a first order reactant, and I would give the equation of natural log of x equals negative kt plus natural log of a naught, and say slope. And we're good. We are good. Okay. So then, based on the data above, calculate the rate constant. Be sure to include units. So, what we would need to do, you could do a couple things. You're going to have calculator, of course. You could go ahead and create the graph, but that's going to take some time, and find the slope, but that may be really fast for you to do. But you're going to need the slope for the natural log of x versus time. Something else we could do is, we know for a first order reactant that half-life is constant. So from our given data, sometimes our data, we can see if it would be 0.1 to start, we want to see how long it takes to get to 0.05. That's not bad. So we could say, from the given data, half-life is 10 minutes, and then solve the equation for K. Now, for units, remember, rate is going to have the units of mole per liter unit of time, and the unit of time here is a minute. So if your reactant is first order, to get these to be mole per liter minute, well, you know that x is mole per liter, and that's going to be to the first power. And so what do the units need to be here to deliver these? Well, this to the first power is already delivering the mole per liter. We just need minute in the denominator. So the units will be minute to the -1 or 1 over minute. Okay, let's move onward. Okay, in a different experiment, the decomposition of y was determined to have the following rate law. Second order. So sketch the graph that is expected to provide a linear relationship. Make sure you label it. You just have to know it's the inverse, and then it'll be a positive, which this, of course, represents our K. Now we're given something else. The temperature of this reaction was increased from 50 to 100. Predict the effect this would have on each of the following. Now, it doesn't say explain, just predict. Okay, so we are increasing temperature. If we increase temperature, we know that reactants have to collide to form product. If we increase temperature, we are going to have more collisions. We are going to have a greater energy of collisions. So we're going to have more and more impactful. So hopefully there's enough, that are going to increase the rate then. So increased temperature equals an increase in the rate. What about the rate constant? Well, this is how temperature increases rate. Now, it would be very unlikely that we would have to find K just knowing activation energy, or find activation energy just knowing K. The Arrhenius equation, it's good for us to know, or it's good for us to just know that activation energy and temperature are what determine the rate constant. Our rate law, where does, temperature come in and activation energy? They come in because they are what determine K. Now, the greater the activation energy, that puts E to a greater power. That will make your denominator larger. That will make this smaller. So the greater the activation energy, the lower the rate constant. But what about temperature? The bigger the temperature, the smaller this exponent. Therefore, the smaller this value, which makes K larger. So when we increase temperature, we're going to increase the rate constant. Usually, a change of temperature of 10 degrees Celsius doubles the value of K. That's pretty substantial. And you can see too, when a catalyst lowers activation energy, when this is lowered, the denominator will be smaller. That'll give a bigger K. So that's exactly how mathematically our catalyst impacts things. Okay, so then it says sketch the graph of the reaction at 100. Okay, well there again. At a greater temperature, our K is going to be greater. What is K here? Our slope. So we might want to write that this is at 50 degrees Celsius, and we want to show a steeper line, and so this is at 100 degrees Celsius. And as long as it's steeper, we are good to go. Okay, so here is just kind of a quote-unquote cheat sheet that is in the NIMSY packet. I'm going to show you two more problems and kind of my thoughts on that, but I thought that was good for us to take a moment to take a look at. This is also good if you want to pause and just take a look at all of this. Not necessarily that I find this tremendously useful, this memorization tip, but if it helps you, please go ahead and use that. What we need to know is this stuff, yeah? And, here's our half-life equations, but this is the one for first order that we're most, asked about, and these will change half-life as the reaction proceeds. Okay, here's a question from 2012. I know it's a little blurry, I'm sorry, it just didn't allow me to snip it very clearly. Okay, so going through this. All right, first, it tells you right away it's first order. Okay, so immediately, as soon as I know it's first order, I know my rate law would look like this, and I know the graph of concentration versus time is that, natural log of concentration versus time is that, per the integrated rate law that is on the equation sheet for a first order reactant, and I know that half-life is constant for a first order, and that is 0.693 over K, also on the equation sheet. Okay, they're telling us that they're starting with 4.70 times 10 to the negative third mole of your reactant in a 2-liter vessel. Okay, I might need concentration, so I'll have to divide that, at 773 Kelvin. After 20 minutes, the concentration is found to be this, lower because it's a reactant. Okay, calculate the rate constant. All right, what am I given? So, I went ahead and found the concentration initially. I'm at this temperature. I'm told after 20 minutes, this is my concentration. Remember, as soon as it was first order, all of these came to mind. How can I get my rate constant? Well, I'm not given information that I can graph. I'm not told my slope. I'm not told my half-life. So, can I use the integrated rate law? I know the initial concentration. I know how long time is elapsed and a certain concentration, and so I can find my K. So that's what I did here. And there we go. And we know when we're taking natural logs, those units don't matter, but remember we can just kind of just mentally think about what kind of unit we should have on K if it's first order reactant. Okay, then we're asked, calculate the initial rate in molarity per minute. So that will be mole per liter minute of the reaction. Calculate the initial rate. Well, that's kind of this, yeah? The initial rate of the reaction at 773, the initial. Well, yeah, I have the initial concentration, and they just asked me for K. So we must just have to plug in our K, know that this means the initial, and there we go. And that's our answer. Okay, and then next. If the inverse of the concentration of reactant was plotted, would the plot result in a straight line? No. We know that the plot will be a curve because if a second order reactant would give us a linear, agreeing with that. No, we need to plot natural log of concentration versus time, and that will give us a straight line. And so we just have to make sure that we're saying. So the plot of what they said will not be a straight line. It will be curved. It will be straight if it were a second order reactant. The plot of this will give us a straight line. So we should really include both in our answer. Okay. In 2004, this was our question. I'm just going to go ahead and give you the answers if you'd like to work through this. So, we're asked to write the rate law. Well, you can just tell from this it's first order. And so, that's it. And they're asking us to justify, so that's why I have the wording, because it agrees with the integrated rate law equation, y equals mx plus b, for a first order reactant. It gives us the linear relationship. Determine the half-life. Okay. We know first order is a constant half-life. And look, we're given a nice beginning concentration of 1. So let's find out where 0.5 would be. Oh, and look, I can nicely read. That's probably going to be 600 minutes. And then I'm just going to check. How long does it take me to get to 0.25? Oh, another 600 minutes. It's just saying determine. So I just have a little bit of wording. And so I just said when from 1 molar to 0.5, it's that. And another half-life is that. There we go. Calculate the value of the rate constant. Now, K is the slope of the integrated rate law relationships. So you could find slope from, this, change in y over change in x, or you just got the half-life. So plug that in, and we get our value for K. So either would be acceptable. I think it might be just easier to use this. So remember, if we're ever stuck, we can look at what we were asked before, and that probably will inform, what to do next. And then determine the concentration after 2,000 minutes has elapsed. I employed the integrated rate law with that as my time, and there we go. Okay, so that, ladies and gentlemen, was, presenting what we need for integrated rate laws for kinetics.